Good evening. I think we are doing exercise 2.2. We have completed how many? 12 sums. So 13 sum now. If one invests rupees 10,000 in a bank at a rate of 8% per annum, how long does it take to double the money by compound interest? We are given that 1.08 raised to 5 equal to 1.47. Write down. Here principal amount is rupees 10,000. Start writing. Here principal amount is rupees 10,000. As rate of interest is 8%. As rate of interest is 10%. We have amount after n years. I hope you remember the formula. We have amount after n years equal to amount after n years equal to, yes, what is that formula? P into 1 plus R upon 100 raised to n, that is 10,000. Substitute the values. 10,000, 1 plus 8 upon 100 raised to n, that is 10,000, 1.08 raised to n. Now what is asked? How long does it take to double the money by compound interest? Here 20,000 equal to 10,000 into 1.08 raised to n, because we are asked how long does it take to double the money. Okay, therefore 1.08 raised to n is nothing but 2. Now you have to use common sense. What is given? 1.08 raised to 5 is given. Okay, we are given 1.08 raised to 5 is 1.47. Can you tell me what is 1.08 raised to 10? Now from 1.08 raised to 5, we can find 1.08 raised to 10 only. See, if you use log tables, you can easily find that. But here we'll try to obtain without using log table. Yes, tell me what is square of 1.47? Type your answer in chat box. 1.08 raised to 10 is nothing but, yes, what is square of 1.47? One student is saying 2.1609. Is it 2.1609? Approximately equal to 2. Therefore, amount, that is money, will be doubled in how many? 10 years approximately. Is that clear? So this is the answer. Now we discuss interesting part, sum of infinite terms of GP. Basically, what is infinity? Infinity is something which is greater than every real number. Note that infinity is not a real number, and therefore we cannot show infinity by a point on the number line. Suppose I ask you to find the sum to infinity of these numbers. 1 to the 4, then 8, 16. See, there is no point in finding sum to infinity because term at infinite itself is infinity. So sum of these is going to be infinity only. On the other hand, if I ask you to find sum of these terms, are these terms in GP? Yes, they are. Now, what is the term at infinity? You will notice that term at infinity is very small number. It is almost 0. And therefore, in this case, sum will approach a certain real number S as number of terms approaches or number of terms becomes infinitely large. Is that clear? And what is the criterion? See, logic is very simple. Here or for this GP, what is the common ratio? 2. So sum to infinity is not defined because it is not approaching a certain real number. But in the second case, you will notice that common ratio is second upon first or third upon second. It is half. That is, you will notice that common ratio is less than 1. So in general, we say that if modulus of common ratio is less than 1, that is -1 less than or less than 1, then sum to infinity approaches a certain real number. I'll give one, in fact, this is the example. We'll try to obtain sum to infinity for this. Okay, can you tell me the formula for Sn? It is A into 1 minus r raised to n upon 1 minus r. Listen to me carefully. I open the bracket. So it is A minus A into r raised what? Okay. A into r raised to n upon 1 minus r. See, we have already discussed the concept of limit. Suppose n approaches infinity. Note that infinity is not a real number. So when n approaches infinity, r raised to n will approach 0 as r or modulus of r is less than 1. We will take one particular example. See, 1 upon 2. This is say r. Then 1 upon 2 square. 1 upon 2 cube. You will notice that this is small, 1 by 2. 1 upon 2 square, 1 upon 4 is still smaller. 1 upon 8 is still smaller. If I ask you to find 1 upon 2 raised to say infinity. So denominator is too big. So 1 upon that, 1 upon this tends to 0. Okay. So in that case, you will notice, see the cursor, this part approaches 0. A into 0 is 0. So can you tell me what is the sum in that case? So sum becomes, I will show you, I will write that part once again. A upon 1 minus r minus A into r raised to n upon 1 minus r. This is the simple formula for geometric progression. Now this part is nothing but 0. So what is the formula for sum to infinity? It is nothing but A upon 1 minus r. See, proof will not be asked in exam. Still, I'll explain the proof once again. What is our aim? Our aim is to find sum to infinity of geometric progression. Use common sense. If the common ratio is greater than 1, then term at infinity is infinity itself. So there is no point in adding terms to infinity because it is not a real number. But if it is a decreasing geometric progression, then you will notice that term at infinity approaches zero, so that sum of the numbers approaches a real number. Therefore, sum to infinity exists or is defined if and only if common ratio, its modulus value, is less than 1. If modulus value is greater than or equal to 1, then sum to infinity does not exist. Then what is the formula for sum to infinity if common ratio or its modulus value is less than 1? First, I have mentioned the formula for sum to infinity of GP. Okay. Now, as n approaches infinity, r raised to n will approach 0. Why? Because r is less than 1. I have taken one particular value, say half. If you don't like half, you cannot take full, but take 1 by 3, 1 by 7, 1 by 11, etc. So say half. Half raised to infinity is 1 upon 2 raised to infinity is almost 0. Right? So this part vanishes. So what remains is a upon 1 minus r. Okay? Still, if you haven't understood, just remember the formula that sum to infinity of a geometric progression is given by s equal to a upon 1 minus r, and it is defined if modulus of r is less than 1, and it is not defined if modulus of r is greater than or equal to 1. Now, what is the use of this concept? See, this concept is used to express recurring decimal as a rational number. Let me explain first. If you have any difficulty, you can ask me after the explanation part. See, 1 upon 2, 1 upon 3. What is the difference between these two? 1 upon 2 is 0.5. We call it as terminating decimal. Can I say 1 upon 3 as 0.3? No. It is to be written as 0.3333 and so on. As 3 occurs bar, we write this as 0.3 bar, or we write this as 0.3 dot. This is called as recurring decimal. Now, using concept of sum to infinity of GP, we can express this recurring decimal as a rational number. I'll explain that, don't worry. See, what is 0.3 bar? As 3 occurs bar, it is 0.3 bar. So I write this as 0.333 and so on. See the next step. Can I write this as 0.3 plus 0.03 plus 0.003? Yes, absolutely right. I have written the same thing. Note that these terms are in geometric progression with small a. First term is 0.3. Can you tell me the common ratio? It is second term upon first term. What is difficult? Division. 0.03 upon 0.3 is what? Don't say 1. It is 0.1. As common ratio is less than 1, its modulus value. Sum to infinity exists. And as per the formula, it is a upon 1 minus r. What is a? First term, 0.3. What is r? 0.1, which is now 0.9. What is 0.3 upon 0.9? Yes, 1 upon 3. So using the concept of sum to infinity of a GP, we have expressed recurring decimal as a rational number. So in short, sum of infinite terms of GP. What is the definition? If for a GP, Sn approaches a certain number S, as n becomes indefinitely large, then S is called the sum to infinity of the GP. The sum to infinity of a GP with common ratio R exists if mod R is less than 1, and it doesn't exist. I'm sorry, this S should not be there. It does not exist if modulus of R is greater than or equal to 1. If A is the first term and R is the common ratio of GP, then this is the formula, right? So open the bracket, split numerator. Now, if modulus of R is less than 1, Then as n becomes indefinitely large, r raised to n approaches 0. And hence Sn approaches the number a upon 1 minus r. This is the sum to infinity of Gp. And in this case, we write a plus ar square up to ar raised to n minus 1 is a upon 1 minus r. Then comes the, see, I have already explained this, recurring decimal as a rational number. See, 0.3 bar means 0.333 and so on. So we could express this recurring decimal as a rational number. Exercise 2.3. First question, determine whether the sum to infinity of the following GPs exists. If exists, find them. We'll be doing first 3, 4th and 5th for homework. Now you need not examine whether the terms are in GP or not, because we are given that the sequence is a geometric progression. So for the given GP, half, 1 by 4, 1 by 8, 1 by 16, first term A is half, common ratio second by first, so it is again half. What is modulus of 1 by 2? 1 by 2. Is it less than 1? Yes, it is. So sum to infinity exists. And what is the formula for that? S equal to a upon 1 minus r. Substitute the values to get sum to infinity as 1. So second, what is first term? 2, common ratio 2 by 3, modulus of common ratio less than 1. So sum to infinity exists. Use the formula, substitute the values to get 6 as the answer. Okay. Now third one, for this GP, first term is minus 3, r is minus 1 by 3. Now you may argue, but minus 1 by 3 is less than 1. See, if r is say minus 11 is less than 1. But here sum to infinity doesn't exist, because mod of minus 11 is 11, which is greater than 1. So you have to find modulus. So it is 1 by 3. Now you have to say, yes, it is less than 1, sum to infinity exists. Now some students put r equal to 1 by 3. No, you are not supposed to put mod r. You are supposed to put r, which is minus 1 by 3. So on simplification, you get minus 9 by 4. Fourth, some homework here doesn't, sum to infinity doesn't exist. Fifth one, it does, and answer is 90. Now, there are 4 sums. I think we will start with second question. Express the following recurring decimals as a rational number. First one is the simplest one. I'll give the answer. It is 7 by 9. And we'll be doing second, third, and fourth. Second, 2.4 bar. That is 2 plus 0.4 bar. See, 2 is not recurring. So it is better that we simplify this separately. Now it is 0.4 bar. It is 0.4444. Sorry. That is 0.4 plus 0.04 plus 0.004 and so on. Note that these terms are in geometric progression with first term 0.4. Common ratio is second by first, that is 0.1. Modulus of common ratio 0.1 less than 1. So sum to infinity exists. So 0.4 dot or 0.4 bar. What is the formula? A upon 1 minus r. 0.4 upon 1 minus 0.1. 0.4 upon 0.9, that is 4 by 9. So from 1, what is 2.4 bar? It is 2 plus 4 by 9. LCM 9, so 18 plus 4. So 22 upon 9. So we express this recurring decimal as a rational number. 2.35 bar means 2.3 plus 0.05 bar. So 5 repeats here. Now 0.0555 can be written as 0.05 plus 0.005 plus 0.0005 and so on. So these terms are in geometric progression. In fact, infinite GP with first term 0.05, common ratio 0.1. Now modulus of common ratio is less than 1. I should write, not less than 0. It should be less than 1. Now this is correct. So sum to infinity exists, right? So what is the formula? A upon 1 minus R. Substitute the value, so 1 upon 18. So 2.35 bar is 2.3, that is 23 by 10 plus 1 by 18 to get 106 upon 45. Right. Last part. 51.02 bar. Actually, they should have given like 2 digits. They repeat 51.023, 2323 and so on. But we have to solve this only. So this is 51 plus 0.02 bar. This is number 1. Now write down 0.02 bar is 0.0222. So this is 0.02 plus 0.002 plus 0.0002 and so on. So as usual, I will say infinite GP. What is first term? 0.02. Common ratio, here I will write directly 0.1. If you want, you can divide second term by first term or third term by second term. You have to mention that modulus of R is 0.1 less than 1. So not term, sum to infinity exists. Sum exists. So 0.02 bar A upon 1 minus R, 0.02 upon 1 minus 0.1. So 0.02 upon 0.9 means 0.90. So that I can directly write 1 by 45. 2 by 90 means 1 by 45. Now put this in 1. I hope you are getting this. So from 1, 51.02 bar, 51 plus 1 by 45. Now tell me what is the answer. Clearly LCM is 45. 51 into 45 is what? Just check this. 2295. Let's check this. So 2296 upon 45. Third sum, if the common ratio of a GP is 2 by 3 and sum to infinity is 12, find the first term. With usual notation, what is S? A upon 1 minus R. Substitute the values. So 12 is A upon 1 minus 2 by 3. That is 12 is A upon 1 by 3. So clearly A equal to 4. Now what is your opinion about sum number 4? Let me read the sum for you. If the first term of a GP is 16 and its sum to infinity is 96 by 17, find the common ratio. I think data are inconsistent. What do you say? Yes, with usual notation, if you substitute the values in fourth one, 96 upon 17 is 16 upon 1 minus R. So that gives me R as minus 11 by 6. What is the modulus value of R? It is greater than 1. So how can we find sum to infinity? So data are inconsistent. Fifth is important. The sum of an infinite GP is 5 and the sum of squares of these terms is 15. Find the geometric progression. Okay. Read on. I'll dictate initial part. Read on. Let A be the first term and R be the common ratio. Let A be the first term and R be the common ratio of infinite geometric progression. Then this GP is A, AR, AR square, and so on. Then this GP is A, AR, AR square, and so on. Sum to infinity of this GP, SUM sum to infinity of this GP is 15. Therefore, A upon 1 minus R, A upon 1 minus R, just check, let me check. It is not 15, I'm sorry, it is 5. A upon 1 minus R is 5. I'm sorry. What is given? Sum to infinity of GP is 5. I'm sorry, not 15, it is 5. So A upon 1 minus R equal to 5. Next line. The sum of squares of the terms of this GP, the sum of the squares of the terms of this GP is A square plus A square R square plus A square R raised to 4 and so on. For this, first term is A square and common ratio is R square. First term is A square and common ratio is R square. Here, sum to infinity is 45. Sum to infinity is 45. Therefore, A square upon 1 minus R square what is that sum? Not 45. 15, not 45, 15. Okay. So this is second equation. I repeat, sum is 5 and sum of the squares is 15. Okay. Now how to solve these two equations? Okay. Now two equations, two unknowns. So we eliminate A. What is A from 1? 5 into 1 minus R. So what is A square? 25 into 1 minus R bracket square. Put this into. Now what are the factors of 1 minus R square? 1 minus R, 1 plus R. Can we cancel 1 minus R? Yes, because common ratio is not 1. So we get 25 into 1 minus r upon 1 plus r equal to 15. Solve this. Cross multiply, divide by 5, open the brackets to get r equal to 1 by 4. So what is a from this? 15 by 4. We are asked to find geometric progression. It is ar square, ar cube. Substitute the values. So finally, what is GP? 15 by 4, 15 by 16, 15 by 64, 15 by 256, and so on. Now 6th sum, find sigma 4 into 0.5 raised to r. R goes from 1 to infinity. 4 is constant outside the sigma notation. R is 1, so 0.5. Sigma stands for summation. So plus next value of r 2, then 3 up to infinity. Now these terms form an infinite GP. First term 0.5. Common ratio is also 0.5. Modulus of common ratio is less than 1. So sum to infinity exists. So what is S? Don't forget 4. So 4 into sum to infinity a upon 1 minus r. Substitute the values to get 4 as the answer. Just a minute. Second, third and fourth for homework. Here I have given the answers. Actually, let me read the third one for you. It may be different in your textbook. It is sigma minus 8. Should I write that? Okay. Let me write sum number 3. Sum number 3 is sigma minus 8. Make this correction if there is any. Minus half raised to r. R goes from 1 to infinity. Okay. So these are the answers. So that's it for today.